Hi, good day. Welcome back to our class in Chemistry 102B. Last time, we discussed on the definition of analytical chemistry, its sub-branches, as well as the importance of analytical chemistry. And I gave you an assignment to read about stoichiometry. Anyway, we have already discussed partly stoichiometry when we were yet in Chemistry 100B. To recall, stoichiometry is the quantitative relationship based on the formula of a compound and the balanced chemical reaction. So let us try to recall these lessons that we have had. Now, let's have first the stoichiometry based on the formula of the compound. For the stoichiometry based on the chemical formula of the compound, we have the percent composition. Now, percent composition is the determination of the individual components of the compound, meaning we are going to determine the percent composition of the individual components or the elements composing the compound. So it would be very important that you should know how to write correctly the formula of the compound. In determining the percent composition, we use the formula percent composition equals the atomic mass of the element divided by the molecular mass of the compound times 100. For example, if we want to take the percent composition of magnesium carbonate, so what are the components of magnesium carbonate? We have magnesium, carbon, and oxygen. In what proportion? We have 1 magnesium atom, 1 carbon atom, and 3 oxygen atoms. So that the correct formula for magnesium carbonate is MgCO3. Now we have to take note of the atomic masses of these elements. So magnesium has an atomic mass of 24, carbon has an atomic mass of 12, and oxygen has an atomic mass of 16. Getting the molecular mass of magnesium carbonate, so we have to add all these atomic masses. So we have 24 plus 12 plus 3 times 16. So the sum is 84. That means the molecular mass of the compound magnesium carbonate is 84. Now, since you're already equipped with the data, we can now solve or determine the percent composition of magnesium carbonate. For percent magnesium, we have 24 divided by 84 times 100. Then this will give us 28.57% magnesium. Then for percent carbon, we have to divide 12 by 84, then multiply by 100, so you have 14.28% carbon. And for percent oxygen, we have 48 divided by 84, so it gives us 57.14% oxygen. If you're going to sum up all their percent composition, it would total to 100%, implying that magnesium carbonate is a pure substance. Then let's go to the stoichiometry based on the balanced chemical reaction. Now, what is important about this calculation based on balanced chemical reaction is that first, you should know how to write correctly the formula of the reacting substances as well as the products formed in the chemical reaction. After writing them correctly, you have to balance the chemical reaction. Well, I have already taught you how to balance a chemical reaction during our Chemistry 100B. That is, you can balance it by inspection. What is the important thing of knowing the stoichiometry based on balanced chemical reaction is that you can determine how much of the reacting substances you should use in order to obtain the maximum amount of product at the end of the reaction. If you are a chemist, then this will serve you as a guide on the amount to be used as a starting material or reacting material so that there will be no much of the waste at the end of the reaction. In the stoichiometry based on the balanced chemical reaction, this will help us determine the mole relation, the gram relation, the limiting reagent, the excess reagent, the theoretical yield, and the percent yield. So those are the uses or applicability of stoichiometry based on the balanced chemical reaction. Now, how are we going to do this? The first thing is, after you have balanced the chemical reaction, we have to set the mole relation. In setting the mole relation, this is to be based on the balanced chemical reaction. So the actual number of moles used in balancing the chemical reaction will be the moles to be used in setting the mole relation. So for example, in the chemical reaction between potassium hydroxide plus sulfuric acid, we have the products formed, which are potassium sulfate and water. If you're going to look at the chemical reaction, the left or the reactants are not balanced with the products. So what will you do? You are going to place 2 before potassium hydroxide and place 2 before the product water. So if you're going to check or inspect, this time you have 2 moles of potassium hydroxide plus 1 mole of sulfuric acid will produce 1 mole of potassium sulfate and 2 moles of water. So the mole relation that you're going to establish will look like this. 2 moles of potassium hydroxide is to 1 mole of 1 mole of sulfuric acid is to 1 mole of potassium sulfate and 2 moles of water. After setting the mole relation, you are going to set also the gram relation. Suppose in this problem, we are asked to get the limiting reagent, the excess reagent, the theoretical yield, the excess reagent actually reacting in the chemical reaction, the number of grams of unused excess reagent, and the percent yield. So in determining all those required in the problem, then we have to set the mole relation and the gram relation. So let's go to setting the gram relation. In setting the gram relation, you have to get the molecular mass of the reactants as well as the products. If you're going to look back to the chemical reaction, since there are 2 moles of the potassium hydroxide, so we have to multiply the molecular mass of the potassium hydroxide by 2. So how do you get the molecular mass of potassium hydroxide? That is the atomic mass of potassium plus oxygen plus hydrogen. And we know that the atomic mass of potassium is 39 and atomic mass of oxygen is 16 and that of hydrogen is 1. So that there will be a total of 56. Since there are 2 moles of this potassium hydroxide reacting, so we have to multiply the 56 molecular mass of potassium hydroxide by 2. So giving us the number of grams of potassium hydroxide to be 112 grams. Then let's go to the next reactant, which is the sulfuric acid. In sulfuric acid, we have to get the molecular mass by, of course, adding the atomic masses of the individual elements. So we have a formula H2SO4, meaning we have to multiply the atomic mass of hydrogen, which is 1 by 2. Then the atomic mass of sulfur is 32, and the atomic mass of oxygen, which is 16, to be multiplied by 4, since in the formula there are 4 atoms of oxygen. So substituting all those atomic masses and considering their subscripts in the formula, we have the number of grams of sulfuric acid is 98, or 98 grams of sulfuric acid. Let's go to the products. Our desired product here in the problem is the potassium sulfate. Now, potassium sulfate has a formula K2SO4, meaning there are 2 atoms of potassium, 1 atom of sulfur, and 4 atoms of oxygen. So substituting the atomic mass of potassium, which is 39, you multiply that by 2. Then add the atomic mass of sulfur, which is 32, plus 4 times 16, that makes up 64, that of the oxygen. Then the number of grams of potassium sulfate is 174 grams potassium sulfate. Let's go to the product water. If we recall, we have 2 moles of water formed. So multiply this water by 2. We know that water is composed of 2 atoms of hydrogen and 1 atom of oxygen. So the hydrogen has atomic mass of 1, multiply it by 2, so you have 2, plus oxygen, which is 16, so you have a total of 18 grams of water. Since there are 2 moles of water formed, so multiply 18 by 2, and that gives us 36 grams of water. So your gram relation will look like this. 112 grams of potassium hydroxide is to 98 grams of sulfuric acid, is to 174 grams of potassium sulfate, is to 36 grams of water. Now, setting those mole relations and gram relations will help you solve the limiting reagent and all the rest of the required in the problem. Now, let's go to the determination of the limiting reagent. We know that the limiting reagent is that reagent which will give the lesser number of moles of the desired product based on the reacting materials. So let us solve the number of moles of the desired product based on the 2 reacting materials. First, we have to solve the number of moles of the desired product based on potassium hydroxide. If we base it on potassium hydroxide, since there are 15 grams of potassium hydroxide reacting with the sulfuric acid, so getting the number of moles of the desired product, you just multiply 15 grams of potassium hydroxide with that of the relation that you have established between the mole and the gram relation, which is 1 mole of the potassium sulfate is to 112 grams of potassium hydroxide. So you can cancel out the unit gram potassium hydroxide, giving us the moles of potassium sulfate. In this case, we have 0.134 moles of potassium sulfate, which is our desired product. Then, we're going to solve the number of moles of the desired product based on the second reacting material, which is sulfuric acid. Since there is 10 grams of the sulfuric acid reacting with the potassium hydroxide, so getting the number of moles of the potassium sulfate, we have multiplied the 10 grams of sulfuric acid with that relation you have set between the mole and the gram, which is 1 mole of potassium sulfate is to 98 grams of sulfuric acid, and this will give us 0.102 moles of potassium sulfate. Comparing the number of moles of potassium sulfate obtained from the reaction between potassium hydroxide and sulfuric acid, it is found out that the sulfuric acid gave a lesser number of moles of the desired product. So, we can say that in this reaction, the sulfuric acid is the limiting reagent. And automatically, the potassium hydroxide is the excess reagent. The next required in this problem is what is the number of grams of the desired product. We know that the desired product is potassium sulfate. And this desired product can be determined based on the limiting reagent. Let's go to getting the number of grams of the desired product, which is potassium sulfate. In getting the number of grams of the desired product, this is based on the limiting reagent. Since the limiting reagent tells us that it's only 0.102 moles of the potassium sulfate which can be produced, so this number of moles of potassium sulfate will be converted to number of grams. To convert the number of moles to number of grams of the desired product, we have to multiply this number of moles, which is 0.102 moles of the potassium sulfate times 174 grams of potassium sulfate is to 1 mole of potassium sulfate, so that you can cancel out the moles potassium sulfate, giving us 17.75 grams of potassium sulfate. Now, we are also asked to get the number of grams of the excess reagent actually reacting. In getting the excess reagent actually reacting, again, this has to be based on the limiting reagent. Since there is only 0.102 moles of the potassium sulfate which can be formed out of the limiting reagent, which is sulfuric acid, so we use that amount 0.102 of the potassium sulfate, then multiply this by the relation that you have established between the mole and the gram relation above. So you have 0.102 moles of potassium sulfate times 112 grams of potassium hydroxide over 1 mole of potassium sulfate. So you can cancel out the mole potassium sulfate, giving us the gram of potassium hydroxide. So in this case, we have 11.42 grams of the potassium hydroxide, which is actually reacting in the chemical reaction. And you are asked in the problem how much of the excess reagent is unused, meaning it's not used in the chemical reaction. Since at the start we are given 15 grams of the potassium hydroxide, and when we determine the excess reagent actually reacting, it's only 11.42 grams of potassium hydroxide. So subtract 11.42 from 15, so this will give us 3.58 grams of the potassium hydroxide, which is unused. So if you're the chemist, do you think this amount is big enough to be a waste or not? So this is already big enough. So that means, had we solved this at the start, so that means after solving this and determining the amount which is unused, so we can at least minimize the amount of the potassium hydroxide to react in the chemical reaction. Then we are asked also the percent yield. Since in this reaction we are told that the actual yield is 16.95 grams of potassium sulfate, so to solve for the percent yield, it is the actual yield divided by the theoretical yield times 100. In the theoretical yield that we have computed, there is 17.75 grams of potassium sulfate formed. But in the actual yield, it's only 16.95 grams of potassium sulfate formed. So, percent yield equals 16.95 grams of potassium sulfate divided by 17.75 grams of potassium sulfate times 100. So, percent yield is 95.49%. So, if you're the chemist, how do you decide your performance in analyzing it? So, is it already good to have 95.49%? Yes, I will say that's already good. So, I have already discussed about the stoichiometry based on the formula of the compound and stoichiometry based on the balanced chemical reaction, and I'm going to give you an assignment through the Google Classroom. Kindly view it there. If you have comments and questions about our lesson for today, you may comment down below. That would be all for today. This is your teacher, Professor Nisitas Ruiz of Holy Name University.